we'd gone into the add method and we'd added in something to chain values in, and it was only just one line of code. Originally we had this second line that said put stuff into the slot at whatever position was required, and all that does is that it just chains new nodes on the front if there happens to be two people trying to occupy the same table position. Okay? And that works just fine because we don't care where these things go in the chain as long as they're in the chain someplace. Okay? Because things are randomly distributed in the table anyway. Doesn't really make all that much difference. Okay? And now we have to update find so that when find comes along, rather than just going and grabbing the thing out of whatever table slot it finds, it's actually going to have to do some checking to make sure it's got the right thing. Okay. What I've also done is I went and made some unit tests, and so there's the unit test to see whether or not you can add a single thing and find it again and see whether something that's not in the table says null. I added one for checking to see what happens when things end up at the same slot. So here's an example of that worker has an ID number, or a small social insurance number that ends in a 5. This other guy has a small social insurance number that also ends in a 5, so they're going to end up being in the same table slot, slot number 5. Now, this unit test is extremely fragile because it relies on knowing that the size of the table is exactly 10 items. Okay? So the only reason that these two guys end up in the same slot is because the size of the table is 10, so that last digit tells you the table position. So this isn't the best way to write a unit test, but it's the easiest and most convenient way for us to just check and see whether or not things work without going to a lot of trouble. And so if you have two people that occupy the same slot, the unit test is basically you should be able to make the looks like one for each of them and find them in the table, find the appropriate thing in the table. I also added something for replacing a duplicate because we said we wanted this thing to work like an array. So if you change the value of a particular item, sub whatever, it should put the same item into the table. It should give you the updated version in the table. So we'll have to do something that handles a check for duplicates someplace in the code. So the test is just add the same guy in twice, and this would be an example of always changed his name or something. So same social insurance number get changed to a different value for his name, and when we find the guy, again, with the fake one, the one that we should find is the second one we put in the table, not the first one. Okay. And finally, I added in another unit test to see whether or not we could get it to work with strings. So here's a simple example of what is one of the reasons why a hash table is called a dictionary, because we're taking a name as a key and some definition or phrase about the thing as the value, and we're trying to associate those things together. Okay, so an associative array or a dictionary are other words for this thing because of that. Okay, so we should be able to have that work also. Okay, so let's go back to the find here. What has to happen with find?
It's got to go to the slot and then traverse the chain.
So it's got to go to the slot first. What's the first issue you can run into when you go and retrieve the node? There isn't one because the thing isn't in the table. Okay, so the easiest case is if the node value happens to be null, then that's easy. There's just nothing in the table, so we'll kick out that case. Okay, so now that we've actually got a node. Now what?
Now you have to check its item, see if it's what we're looking for. Or just the key?
it could be a whole chain of things, so we're going to have to run a loop down the chain of things. So maybe a better word for this thing is current, just to give the sense of running through more than one. So I'll change this thing to current. And so now this becomes a loop of while current is not equal to null, we're going to have to do some stuff. This is the if we found the one we're looking for. How do you know you found the one you're looking for?
The key matches.
If current dot wherever it is, what did I call it? It's hiding in the node someplace. Current dot stored item. No, that's oops. Oh, well, we have to dig out the pair first. So we'll do that first. So there's the pair. That's why we don't like it. If a pair dot, well, why don't we dig out the key just to be nice here. So we'll get the key. And if the key matches, so what are we going to use for matches? Dot equals, oops, we'll call that pair key. So if the key equals the pair key, then we found the right thing that we're looking for, so we can return the value out of that thing. Otherwise, if we didn't find the one we're looking for, what happens? Have to advance, so current equals current dot next, and we'll run source format on this to make it look pretty. And we should end up with something like that. Okay. Notice that this test is actually sort of unnecessary, because when you get down here, if you haven't found it, you're returning null anyway. But I don't mind leaving it in there just to kick out the obvious empty case and not have to worry about it. So run through the chain of things and use equals. Notice that in this thing, we use hash code all the time in the object to find its table position. And so we use the keys hash code, and then we use the keys equals. Okay? We had to write hash code specifically for objects that we want to put into this hash table. Equals is just the standard equals, but it brings out a really important point about hash table, about putting things in hash tables. The key that you're putting into the hash table has to have both a hash code method and an equals method, which generally means you have to override both if you're writing your own class. Okay, so we've always got into the habit of overriding equals for our own class, but now you also have to override hash code for your own class. So if you plan on putting a student value into a table and you're going to use the student as its own key, then student has to have both equals and hash code because they're both used. Okay? So don't forget to do that. If you forget to do that when you're putting student against student into a hash table, it won't find things. Just like the same thing we've gotten with index of searching for something. If you haven't written equals, you won't get it. The other interesting thing about hash code is that you have to use exactly the same fields in hash code that you use in equals. So if you say, I think that students are the same by their first name, last name, and, I don't know, social insurance number, then if you do that for equals, then hash code has to use those three same fields when it does its calculation of values. Okay? They have to be identical. If they're not, if you don't use the same fields, you'll get all sorts of weirdness happening, because hash code and equals are basically two ways of determining identity. And so if you use this information to determine identity for equals, then you have to use that same information to say, I think this is a match for hash code. Okay, so there's the find, either finds a matching one and sends back the value, or doesn't find a match. And let's just see how we do so far in our unit tests. Let's see, it doesn't find a lot of stuff, does it? Let's just see where add and find breaks down. So we add A to the table, and then we try to find somebody with a 1, 2, 3, and it looks like it doesn't find them. Okay, well, that's fine. Let's just put a breakpoint in add find. Let's run with the debugger. Let's go find the table. And if you look in the table, you'll see that it has 10 available node variables, which are all probably currently empty. There's no table there. Now, I'll just try one. We'll just do a step over. So we added it to the table, and there we go. Let's just crack it open and see what we've got. So what position should that thing have ended up in?
Third slot.
Third slot. So we'll go into table at position 3, contains that thing. And if you look at the stored item is A with the SIN number of 1, 2, 3. So it made it into the table. It's fine that's dying for some reason. Okay. So while we're here, since we're going to do a find coming up, we'll go in here and we'll put a breakpoint in find, and we'll hit resume, and we'll see what happens when it finds it. So we get the hash code. The magic number is the 1, 2, 3. That's correct. We mod it with the table slot size to get slot number 3. We go and we pick out the current value. So we'll do a step over there. Current has a value of current next is null. The stored item at that position is, let's just take a look. So it found the right node, step over. Current isn't equal to null. Current still isn't equal to null. It gets the pair. It gets the key. And let's just see what that thing is. And the pair key is, let's check and see what its value is. There's the 1, 2, 3, and the value of the key. Well, let's just do a step over. Didn't match. So equals between the key and the pair key didn't match. But the values for them are
Is it because they don't point to the same memory location?
well, the key is equals, so let's just go take a look, kill that thing off, and we'll go take a look in
Paranoid?
worker. What's missing in worker?
How many
Equals.
No equals. Okay, so there's that rule. Have to override both hash code and equals now. So we'll do that, and then we'll return, what do we want? Sin dot equals, or sin double equals in this case. Hang on. Okay, so the social insurance numbers have to match, and now we'll try the test again. And now we've got find and replace duplicate work. It doesn't work on strings. It also doesn't work on the same slot. So let's just go down to the same slot guy. And what happened here is I added the new version. Oop, is that? Says it didn't find the one I was looking for. Okay, review the test here for a second. This is add something at what basically amounts to table position 5, add another guy at table position 5. So now they should both be there. Then try to find the second guy that was added, and that's the thing that dies. Put a breakpoint there. Run with the debugger. Get rid of the old breakpoint. Hit resume. We'll get rid of that one for now until we get to the correct unit test. Hit resume. This is finding people in the same slot. I think we'll get lucky with a step into. That's the constructor, so we can do a step out of that. And another step into to get into find. So let's just see what it's doing. So current is not equal to null. It grabs the stored item. It grabs its key. Are you expecting to find it or not? Should this one match or not? Go back and look at the unit test here for a second. So we added in B, so we should have two people at the same table position. Let's just go look and see if that's what's happening. Table slot 5. We'll go down and look at table slot 5, if I can find it in the array. There's our table. There's position 5. 5 contains the first stored item, which is, get it right, which is the guy who's B,
Second one.
or sorry, the second one, which is B, which is correct, right?
Yep. Some would have been inserted in front of
and we'll check and do a step over and see whether or not they match. They match, so it's sending back the value, and when we do a step over, the test is wrong.
Why is it matching?
Yeah, we'll just see here. Let's do another step over. Test is wrong. Should be second placed. Right, it should find the second one first. So there we go. There's the joy of getting bad tests. They take a long time to figure out what's wrong. So that should be found. Should actually be found second. I'll just change them around so that they're consistent.
It is found first,
Yeah, bad names.
because the first one put in will be the second one found, because it's the end of the chain.
995 should be equal. 995 should be that guy, right? And this guy is found 555 and found 555. Does that help? Equals first. That look better? Okay, we'll run that thing. See how we do. I can never locate the test properly. And so now we've got everything working, except for some reason it doesn't work on strings.
Yeah. Because equals is just checking the sin. You're not using strings for keys.
Okay, let's look at this test. This is just string versus string. So when we add something, we're actually using Robin's as the key. So that's Robin.hashcode is the thing that gets used to find them in the table. Okay? And when you're searching for a match to see whether or not you've matched one, it's Robin's equals.
Which doesn't exist.
Strings have both equals and hash code by default.
But when you add, you need the table slot, so when you divide, you bring another memory address.
Let's just go take a look here. Look at the table position. It's -8. Why would it be -8?
With the hash code. Might have some weird.
Strings hash code actually can generate negative numbers. Don't ask why, but that's what it does. Okay? Because a negative number, as long as it's unique, still uniquely identifies the thing. So the definition of hash code actually says it doesn't necessarily have to be a positive number. I could say -23 uniquely identifies me, and that's a valid integer.
But you can't use that with a hash table.
But you can't use that with a table, so what do we have to do with our code? When you get a hash code,
You have to check to make sure that it's a positive number.
or
You
just
make it positive.
always make it a positive number, which is math.absolute of whatever the hash code happens to be. And I'm sure I've got one more in find, so we'll do the same thing to find. Key is actually math.absolute of the key. And one more time. And there you go.
Circle.
Okay. So notice that hash table isn't a huge pile of code. That's it. But it's extremely efficient at finding things. Okay? So now that we've got the code, let's try a couple of different examples with actually using it. The first one I want to do is one to look at command line arguments. And I think we actually did this one last year for, or last term for, just to show you how scanner worked. And maybe you'll remember it if I start adding a little bit of the code. Let me just find this thing here. We'll make a new class. And it will suddenly start to become very clear to you, I think. Let's just do this. Oops. Okay. So what I've got is
Two-dimensional array.
a two-dimensional array of strings. Actually, let's start out, I'll just add this one extra line in so that you can see what we're doing. And change that to an S. We did this one before in the previous class, where what happens is you've got some set of arguments that are coming into a program. So these could be command line arguments, or these could be, yeah, I know, it's okay. These are command line arguments, or they're from a web browser where you get key value pairs, anything like that. And so what you're given is just a string of these things. And let's assume they're command line arguments. Well, here's a set of defaults for what the command line arguments start out as. So think of this as a Linux program. If you don't apply any parameters to the height for whatever command this is, then you get a default height of 20. Right? If you don't apply anything to size, you get a default size of 10. So those are all the defaults for this particular set of arguments for the program. But what happens is when somebody does the arguments on the command line, they want to change some things from the defaults. So in this case, instead of a size of 10, they want to change the default and make it size 100. Okay, and the same for height. They don't want 20, they want 25. The name, they want to change to Joe from empty, and in this case, they want to leave the weight alone. Okay, so now the question is, given that those are the things that you want to change, and those are the defaults, how do you get all of these things done in the program? Only change 2 of 3 or 3 of 4 in this case in order to make it work. Okay. Here's the sneakiness of hash tables. Hash tables replace duplicates. Okay? So what you can do is you can put all of these things into a hash table to begin with. So associate height with 20, size with 10, weight with 50, etc. Get those initial values into the table. And then if you take these values and also hash them into the same table, it will replace any duplicates. Okay? And rather than bothering even to parse this command line, let's just run through it the easy way, and I'll just make key value pairs afterwards for these things instead of parsing the line. So let's go through and let's make and I'll use the official Java stuff here. So hash table in Java is called a map. And we're going to map string to string like we did with our last unit test. And we'll call this a name table. New hash map. And we're going to take the hash map, string against string, etc., to start with. And I have to do the import statement for both of those. Okay, and then I'm going to run through all of my items in the table. So defaults is the table. A row corresponds to each row because it's the first subscript in the table. Okay, so I'm going to go through each one of those, and I'm going to, just to show you what happens here, I'm going to say that the value is whatever's in row sub 1, and the key is whatever's in row sub 0. And then we're just going to do name table dot put of the name, the key and the value. Okay, so that's a for each working on this table. It's going to take every single row of the table, because for each is operating on the rows of things there, and it's going to plug in the key of that and the value of that into the table. Okay. Now suppose I do something like do name table Want to see what's in the table? Sure, why not? There's a good idea. Here's an interesting thing. Suppose that I want to see everything that's in the table. If I do a for each on the table, what am I going to get out of the table?
All the rows.
This is a hash table. What did we put into the table? Two things, a key and a value, and in our code we paired them up. So if you extract things from the table, what are you going to get back? Pairs of things. So we need the pair of things coming out. The pair of things is actually called an entry of, in this case, string against string. For every entry in an entry in the name table, we're going to do something. We'll print out the key and the value. And this one is one that exists in the documentation. Eeks. Gotta go find it. Probably do it this way. Map dot entry. There we go. Okay. So there's the map thing, and the entry is what they are calling, what we would call a pair. So for every map entry in the name table, think about this for a second. Oh, in name table dot, oops, just to make my life difficult. That'll do it. This takes a little bit of explanation. If you put pairs into a table, what are the three different ways that you can do a for each on the table? It's actually three different things you can get out of the table. We're getting the key value pairs. What's another thing that you could look for in the table? just the keys or just the values. So there's 3 separate ideas that you could do for a for each. I want to go through all of the keys, I want to go through all of the values, or I want to go through all of the pairs. And so for a hash table, you can get out each of those things, okay? So in this case, entry set is give me all of the pairs. There's also name table dot keys and name table dot values to see each one of those. So we'll go through all of these, and we'll do print line of what the heck, and entry. If we're lucky, it's got a 2 string. Let's just see what it does. Oops. Doesn't like my driver. Oh, yeah, a main would be nice, wouldn't it? Let me just steal the main here. Oops. Ah, making a mess of that, aren't I? In both places. One more time. New arguments driver, so we'll call the constructor. There we go. Run the thing, and the stuff that we've got in the table. So there's the table so far. Okay, so all of the defaults are in there as defaults, no name. Let's do this. Wrong place. Name table dot add, and we'll do name with Joe. There's a semicolon in there somewhere. Come on. Put. By the way, why is it called put rather than add? Most of the other collections we've seen would use it.
Differentiated.
To differentiate it, because this is one that requires 2 arguments. So there's that idea that hash tables are different. Every other thing you say just add and it's just one thing. This one is called put because you have to do 2 things. There's the key and there's the value. And I put that in the wrong place too, didn't I?
Yep.
Oh yeah, mouse is giving me a hard time today. So if I put that thing into the table and then I print them out again, I actually get a print line in there? Nope. So we've replaced, we should have put a value in for Joe, so we'll just run that thing. And there's name has been replaced with Joe. Okay, so you could replace anything that you wanted, so you could basically parse that line. You could do size. Oops. Bad day for typing. I can't remember what the default was. That'll be a lot bigger. And run it again, and it's changed. How would you handle the case of people mistyping things? What happens if I mistype something?
Create a new
Like if I do this. What am I going to get in the table?
Maybe get an extra value.
Going to get an extra value. We'll run it.
The size, which is default, and then SIS, which is your value.
Oops.
So you have to check that if something doesn't exist.
So what we need to do here is we need to say if for some reason name table dot, which one?
The key.
Contains key key is false, meaning it doesn't exist in the table. Print out a message. Could make the message better, but bad argument. And then since that's a special case, we'll just keep adding things in. Except I put that in the wrong place, didn't I?
Yeah, put in the name. Don't have all three.
It's time for a reboot to get my mouse to.
We have a bunch of places.
Yeah, I'll just come down here. This isn't the actually the. There we go. I think I got that in the wrong place too. Oops.
Yeah, that one above name table got put needs to be taken out.
key value.
This one here. Oh, that brace. Got it. Thank you.
Doesn't the if need to go inside the code?
Yeah, this is, yeah, what I was gonna do is I was gonna run a loop through all of this stuff. And so this isn't the best example because this would actually have to go inside a loop. So I'm just gonna, rather than even doing the loop, I'm just gonna leave it like that and remind you that if you were processing all of these arguments one at a time, you would actually have to go through and check and try to pre-enter them with contains key just to make sure they were okay. Okay, so rather than doing the error, I'll leave it at that. Okay, so the point of this thing was to say, you know, basically hash tables replace duplicates. They work exactly like arrays. So that's the joy of using these things, is that it makes your life really simple when you wanna do this sort of processing, right? Start out with a set of defaults and then add or change things afterwards. That's something that you'll find quite often used for hash tables. And notice also that I'm also going to remind you that when you read a lot of these examples, people use strings forever in their examples because string gives you equals and hash code by default. Okay, and so be wary when you're reading sample code, because if you're using your own object as a key instead of string, you have to write hash code and equals in order for things to match properly. And if you don't, you put stuff in the table and you just can't find it again. Okay, or it doesn't do what it's supposed to. So we'll look at some examples later where they sort of do the simple thing rather than showing you a decent example. Okay. So the example we'll look at tomorrow, I'm going to do one where we have to use a thing as both a key and a value, and we have to write our own equals and hash code and show you how you use a hash table to do some other interesting things. Okay. And with that, we're out of here for today.